Olá! A IUPAP, International Union for Pure and Applied Physics, está interessada em muitas coisas. Dentre elas, a definição das unidades básicas que nós usamos no dia a dia, a manutenção das constantes fundamentais, mas também está muito interessada nos desafios que a ciência tem atualmente. Na área da física são muitos os desafios. Nós temos desafios desde o entendimento das partículas elementares, da matéria condensada, na física nuclear, na biofísica, na astrofísica. Em todas as áreas, ou sub-áreas da física, nós temos desafios. Para que você saiba quais são esses desafios, a IUPAP organizou um workshop especial, que chama-se Entendendo os Desafios da Física Moderna. Cada área da física está aqui sendo apresentada por um líder, membro da IUPAP, e que você terá então agora a chance de entender, através desta apresentação, os desafios que a área apresenta e como os físicos, de um modo geral, estão superando esses desafios para que a física seja um instrumento de entendimento das ciências naturais e que auxilie o homem não apenas a avançar o seu conhecimento, mas a tornar a ciência um instrumento útil da melhoria de vida de cada um existente nesse planeta e nesse universo. Assista e também faça parte do entendimento dos desafios da física moderna. Boa sorte!
So the next speaker is Minh Quang Tran from C16, and he will speak about the quest for fusion.
Yes, okay, thank you very much. I shall try to guide you through the quest for fusion and talking mainly on two devices, the ITER and demo. So the plan of the talk would be first, I think that it is an important challenge, the energy question, and maybe how fusion can try to answer this question. And finally, I would like to talk a little bit about towards the industrialization of fusion based on magnetic confinement through the Tokamak concept, ITER and demo. What I shall not talk is about other concepts like stellarator and inertial confinement, and of course plasma physics covers many of the fields which I shall not have the opportunity to share it with you. So energy and fusion, I think that we should say a few words about why energy is an important issue for us. First of all, the population increase. We shall be around 11.2 billion at the end of the century. We have a change in the energy mix, and also more and more electricity will become the workhorse for our use of energy. And of course, also, we need to have sustainable energy, and in this sense, environmental effect, safety, and the issue about the legacy towards the next generation, namely not to have, or try not to have disposal which are in the geological period. Of course, you know that the main reaction that we shall try to use is deuterium tritium. Why? Because it's quote-unquote the easiest way to realize fusion. But while I'm saying that it is the easiest way, it is not so easy. But before we go into the topics, let's see why fusion is a disruptive energy. First of all, fuels are inexhaustible. Deuterium is very abundant in the water, but tritium is a short-lived radioisotope, so we have to breed it, and we breed it through using the neutron which is produced by the DT reaction, and making another fusion reaction with lithium, and you regenerate the tritium which you just have used. And why I also say that it is disruptive energy, because it has some inherent safety aspect, no chain reaction, no large amount of afterheat, because if you can use low activation material, the amount of heat which you produce inside the reactor, if you shut it down, will be relatively small, and we could avoid incident or accident like the Fukushima type. And naturally, the amount of CO2 which is liberated per kilowatt hour, and I think that this is important. We have to run the full life cycle of the plant, and this amount of CO2 per kilowatt hour is relatively comparable to all the renewable energy. So why is it so difficult? Here you see it immediately that the reactivity of the reaction, which is computed like sigma, the cross-section, multiplied by the velocity of the particle, is maximum at about 100 million degrees. If you talk about kilo electron volt, it is between 10 or 20 kilo electron volt of temperature. So how do we use fusion? We have here a body which is at 100 million degrees, so it loses some, let's call it heat, and then you just have to make the balance between what you lose and what the reaction can produce. This is the simple way of describing the Lawson criteria. And after some relatively simple calculation, it ends up with an inequality. The number density of particle inside the volume multiplied by the temperature, multiplied by the energy confinement time of your plasma should be larger than a certain value, which is 5 times 10 to the 20 particle per cubic meter, kilo electron volt second. So we have to create a plasma with N in the magnetic confinement of the order of 10 to the 20 particle per cubic meter, and T about 100 million degrees, and the confinement energy is a few seconds to satisfy this Lawson criteria. So we have then what is the state of the matter at 100 million degrees. Already at 100,000 degrees, we have the plasma state. So we deal with plasma, and the fusion products, we have a helium-4, which is a charged particle, which will be confined in the machine, and the 14 MeV neutron, which will escape out of the plasma. And we shall use energy, kinetic energy of the neutron to first produce the tritium, and secondly, also to recover its kinetic energy so that we can produce electricity out of it. I shall talk more longly about the production of the tritium, but you can see that here we have two fusion reactions, one with the lithium-6, which is exothermic, and which has relatively large cross-section, as you will see, and one with the lithium-7, which is endothermic. Unfortunately, we have to enrich the lithium because in natural lithium, we have the majority is lithium-7. So how do we confine a plasma? A plasma is a collection of charged particles. The way to confine it is through magnetic field. Electric field doesn't work just for the simple reason that we have the Debye shielding of when you have a plasma. If you put an electrode inside a plasma, for example, a negatively charged electrode, ions comes towards the electrodes and electrons are repelled. So at the end, it forms a Debye shielding around this electrode, and there is no electric field inside the plasma. So we have to use a magnetic field, and we use it through the Lorentz force. And how is the magnetic field produced? It is through the Maxwell equation, curl B equals to mu naught J. So how do we describe a plasma? It's relatively simple as well. You have various models to describe the plasma itself, MHD model, fluids in plural model, or kinetic model. And of course, in all these fluids equation or kinetic equation, we have E and B, which is just given by Maxwell equation. So we have a set of equations that we have to solve. Simple. And then, now you try to confine the plasma through the principle I just said. The best way of doing it is through the so-called Tokamak concept discovered by our Russian colleagues, which consists of having a toroidal magnetic field created by the coils, which you see on the picture, but also you need that the plasma itself carries a toroidal current, which produces a poloidal field, and it is a combination of the toroidal field produced externally and the poloidal field produced by the plasma, which confines in the plasma itself. This is the Tokamak concept. And how do we heat the plasma? Also, basically relatively simple. You can inject electromagnetic wave inside the machine, and it is a principle of our microwave oven which works here. We have then various types of waves, for example, very high frequency waves, which corresponds to electron cyclotron frequency, the ion cyclotron frequency, and if now there is another trick. You can try to inject inside the plasma particles, which has an energy which is much larger than the 10 keV of the ions which exist in the plasma, and you hope that through thermalization you will heat the plasma. But you cannot put charged particles inside the plasma because they will not enter. So you have to put in neutral particle so that they can enter the magnetic field. This is called neutral beam injection. And all these three processes that I mentioned to you, you can also drive current, this famous toroidal plasma current, which ultimately needs to be sustained, otherwise it decays due to the resistivity of the plasma. So we have heard today many times about the Moore's law. In fact, research in plasma, if you take the measure of the achievement through the NT-tau criteria, which I mentioned to you, you see that the curve, we also achieve something more or less similar to the Moore's law. And we are, if you look at the small dot on the right-hand side corner, ITER, we are pretty close to the region where this criteria of Lawson is fulfilled. So what are the challenges? We have the challenges of physics. It's how to confine this plasma when you have such a large amount of heat which is produced inside the plasma, and how to control the heat removal from the plasma. And there is a long list of technology problems. The first one, I would say, it is the self-sufficiency of tritium. Materials problems and high heat flux materials as well. So what is the roadmap? The roadmap, as you can see here, has two main elements before reaching the fusion power plant. The ITER, which is under construction, which will produce about 500 megawatt of thermal power to be followed by a demo machine which would then produce something about 500 megawatt electrical power by the mid of this century. So let us talk very quickly on ITER. Here is a beautiful picture of ITER. Its objective is to produce 500 megawatt thermal power during 400 seconds typically, while you inject inside the plasma about 50 megawatt. We need to study the physics of a plasma when you have a large amount of power which is liberated by the 3.5 MeV helium, which is about 100 megawatt compared to the 50 megawatt of external power. From a technological point of view, it is the first time that we integrate in a single machine all the technological component which is needed for a machine. And finally, we need to prove the safety aspect of a fusion reactor, and I can say that ITER is the first fusion machine which is licensed by a nuclear authority, as a safety authority. In fact, it is a French safety authority, and it is considered as a reactor in the nuclear sense by the French authority. So here is just the same summary that I just mentioned to you with some of the dimension, and we can discuss it afterwards. But the interesting point here is that this famous toroidal current in the plasma that we were talking about is about 15 mega amp, which is carried by this machine. Here, I just want to put up an electrical power consumption. We call in our jargon the electrical power consumed by the machine during the 400 second or 1 hour pulse, the pulse power which is drawn from the electrical network, and it is about 300 megawatt. If you add to this about 100 megawatt of steady state power to maintain all the other equipment running, we are about 400 megawatt electric, and we shall produce 500 megawatt thermal, taking a typical efficiency of a factor of 1/3. One can say that ITER is about a factor of 1/3 from break-even. And the ITER schedule from the director of ITER is that the first plasma will be around 2025, and the DT, the full deuterium-tritium operation, is 2035. Now, after ITER, we are already preparing in the demonstration reactor, which will produce electricity by 2050. And again, what are the objectives of demo? Demo, at least in Europe, will produce about 500 megawatt electricity. It will have to show self-sufficiency in tritium with a tritium breeding ratio of larger than 1, so that you can compensate and create more tritium than you need so that you can have tritium for the next device. And we have to satisfy all the technological aspects, such as reliability, availability, maintainability, inspectability. We have to use low activation materials. We have to have, here in this case, what we call balance of plants, namely all the auxiliary electrical system. Okay, we can skip this device, but I just want to point out to you that the thermal power produced in demo would be of the order of 3 gigawatt thermal to produce about 500 megawatt electrical net to the grid. Let us now turn to the tritium breeding issue. I have promised to you that I shall show to you the cross-section of production of, for the reaction lithium plus neutron yielding lithium plus neutron yielding tritium. And you can see really that if you use lithium-6, the low energy part of the neutrons will give you a lot of, a very large cross-section compared to the lithium-7 cross-section, which has a threshold because it is an endothermic reaction. So we need a tritium breeding ratio larger than 1, but we have only 1 neutron. So we need a neutron multiplier somewhere, which could be beryllium, lead, or lithium itself. And the main available tritium breeders are not liquid lithium, but it is some mixture of lithium, which could be a lithium eutectic, lead, and lithium. And the coolants could be pressurized water, helium, or CO2. This to increase the operating temperature and increasing the thermodynamics efficiency in the balance of plant. Now, I would like to share with you a few concepts about the materials. When a material is hit by the 14 MeV neutrons, there will be formation of Frankel pair, which will have an effect on the mechanical properties. The second point is that you have embrittlement by helium and hydrogen formation through the two reactions with iron, which is on the screen. So we have here a very delicate balance between the hydrogen and helium production and the mechanical defects due to this Frankel pair that I have mentioned to you. We have, for example, about 10 APPM of helium production per mechanical damage, as I described before. So we need a specialized 14 MeV neutron source. And here, okay, we can skip this because you see here some metallurgical typical curve. There are two effects: the hardening, loss of ductility, loss of fracture toughness, loss of creep strength, swelling, and the second effect due to the embrittlement is the change in ductile to brittle temperature. So we need there a neutron source which is specific to produce 14 MeV neutron. And this is done through the reaction lithium with a deuterium beam of about 40 MeV, and then it can produce a certain number of neutrons. And the principle is relatively simple. You have an accelerator of deuterium, 40 MeV, which falls into a liquid metal target and produce the neutrons, which has roughly the acceptable spectrum for our need of testing the material under 14 MeV neutrons. So let me conclude. This sentence is a famous sentence, at least in our community, which is attributed to academician Lev Arsimovich. I would really like to have it in Russian once in my life, so I beg my Russian colleagues to help me. But I think that besides this joke, I think that the worldwide program has now two focus: ITER, which is a 7 parties program, and the step after demo, which is also pursued by many countries like China, EU, Japan, Korea, And my own view is that we really need to go through this exercise so that at the end we know what are the problems and how to solve them. Thank you very much.
Thank you very much for providing this great perspective. Questions, comments?
I'm just curious, you haven't talked about, as you scale up, nonlinearities and instabilities. Do you feel like those problems are solved as you...
No, okay. In a plasma, the plasma contains a large amount of free energy, if you like. So instability exists in plasma. Instability in plasma will grow nonlinear, and it will induce turbulences, and turbulences will induce, in turn, loss of energy and loss of particles. But fortunately, right now, with the power of computers, we start to be able to simulate from first principle, let me call it this way, the nonlinear stage of turbulence and deduce from it the heat diffusivity in a machine of the size of ITER.
Further questions? I don't see any. Thank you very much again.